This is episode 6. In this episode, we're going to look at 3 different vulnerability types. Number 1 being a logical vuln, an authorization vuln, and all the way at the end, we're going to look at the re-entrancy vulnerability. I think that's what it's called, where it was discovered in a DAO attack, and hackers were able to steal millions worth of Ethereum, and that's what it was discovered. All right, let's roll it. Hi Pablo, thank you again for joining me. Last time we chatted, we talked about, we looked at threat modeling, and you gave us an example of an ERC20 contract, and that we kind of pretty much talked about how attackers could steal tokens from others without their knowledge, and we kind of like walk through it. Tell me, what do we have going on for this episode?
Well, we're going to talk about, first of all, thank you for having me here again. And we're going to talk about the most common vulnerabilities, or the most interesting vulnerabilities in blockchain in general. And and we're going to see some vulnerabilities in Ethereum in particular.
Cool. What are these examples? Like, what are the vulnerabilities that we're going to look at this time?
We're going to see, we're going to talk about pretty complex vulnerabilities regarding with signing transactions and all of that. But the thing that we are going to see technically is called re-entrancy attack, which is pretty interesting. You can drain all the funds from a smart contract, all the funds.
Why does that sound so familiar? Is that something that's happened recently?
Yeah, recently, most blockchains are trying to secure their contracts to not allow these kind of vulnerabilities for sure, because this is, I would say that this is the RCE of the blockchain, because you can drain everything in a smart contract. So right now, smart contracts are more secure, but probably you have heard about the DAO hack, which happened in 2016, and it produced lots of losses.
Wow. Okay, we'll get back to that. Let's talk about it. So let's start with the first vulnerability, and then we'll keep the best for last.
Yeah. So the first thing that I want to bring you is the vulnerabilities regarding with authorization. So
Okay.
these vulnerabilities, of course, they are related with traditional IT authorization vulnerabilities, but in this particular case, um, they can just with one word you can create a critical vulnerability. Why? Because you have in Solidity in particular, you have describers of the functions. You can specify the visibility of the functions. So you can specify that a function inside a smart contract can be public, private, or external. We are not talking about external ones, but of course, if you change that visibility of just one function, and that function maybe is managing funds, maybe is, I don't know, withdrawing funds to the one that is calling it, you are allowing everybody to call that function and drain all the funds. So just one word can make a function, can introduce in a function a critical vulnerability. So, um, also, in order to avoid these kind of things, you can use what is called modifiers, which are also one word that could be, for example, only owner, that you can put it in the function and make the function only callable by the owner of the smart contract. So you are securizing that function with just one word. Also, that is why sometimes developers miss these kind of things, because it only relies in one or two words. That's pretty critical.
So, do you happen to have an example of one of these that we can take a look at, maybe?
Yeah, we can see the previous video functions, and just let me 1 second. Here we have the ERC contract that we had in the last video,
Yeah.
and as you can see here, we have the main function, which is set as external. So everybody can call this function and mint to himself tokens. Okay, so
Okay.
we can set this function to public, which is going well, it's going to do the same. Everybody can call this function. So if you are creating a private token, I mean, for example, I'm a protocol that wants to sell my tokens. I don't want this function to be public because I want to be the one who mints the tokens. I don't want to give free tokens to everybody. So one thing that I could do is just make it private. So this means that this function is only is going to be called from the self contract. But if you want to call it from outside, for example, from I don't know, from the owner wants to mint tokens, we can put it as public, but we can use a modifier. A modifier is only owner, only owner. So with this modifier, what we are doing is specifying that this function only is going to work if the owner of this contract is calling it.
Okay.
So you are putting one layer of security that is going to avoid. Okay, everybody is going to be able to see this function, but only the owner is going to be able to call it.
So when you say one word, you literally mean one word has to be added to that line, and that could be going from vulnerability to nothing, pretty much. Like it could be fixed by doing that.
Yeah, that's right. You are only using, well, in this case, you can use two words: public, private, well, three, or only owner.
Wow.
You know.
Is this specific to a particular technology, or is that could that happen to any contract?
Well, this is specific to Ethereum because we are developing in Solidity right now. We are seeing a contract in Solidity. This is not happening in Rust, for example.
Yeah.
No.
So anything that's developed in Solidity could pretty much, if people are looking for this type of vulnerability, Solidity be a good place to look for because the way you specify it is in Rust is different.
Well, yeah, but in Solana, for example, in Rust, you have to take into account the ownership of the accounts, for example. So you have also authorization vulnerabilities regarding the Rust language and the technology of Solana, for example. You have to check if the owner of the account is allowed. Well, if the one that is trying to modify an account is the owner or not. And yeah, and this is happening in every blockchain with different
Ah, okay.
technologies. You
Okay,
know.
very cool. You
Mhm.
said something about looking at technology specific vulns.
Mhm.
What does that
Yeah.
mean?
Well, for example, the thing that we saw in the past video, when we talk about minting and transferring funds and all of that, that vulnerabilities they are not happening in regular IT, But
Yeah.
also we have, for example, two kinds of vulnerabilities that I would like to talk about. That are, for example, the voting power related attacks. So in Solidity, well, not only in Solidity in Ethereum, but in every blockchain, you usually have uh, governance contracts. That contracts allow a user to vote the the path that the user wants the protocol to take. I mean, um, if you are the owner of the tokens of a specific protocol, you can propose modifications in the protocol and you can vote for modifications in the protocol. You can change the behavior of the protocol by voting, you know.
Okay.
For example, I don't know, I want to implement a new function um, that is going to be called whatever, and I create a proposal, and other users, other uh, stakeholders can vote for that proposal. So um, the thing is that you have to to have tokens of that protocol to vote. Okay, so if I want to modify the behavior of the protocol and I don't have voting power, I don't have tokens, I can, for example, perform a flash loan. A flash loan is a loan that is pretty fast.
Yeah.
Okay, so I ask for tokens, another protocol give me that tokens. I use that tokens to create a proposal or vote for something, and in the same transaction, I give the tokens back. So I am modifying a protocol behavior without, in fact, being a part of it. So this would be a pretty interesting attack that can happen and that sometimes happened in the wild. And well, if you want to create a remediation of this attack, for example, you can set a timer. Okay, you can only vote in this protocol if you have held tokens for 1 week, or 2 weeks,
Yeah.
or you know,
So you
and
implement it by giving it a time requirement, so you can't just do a flash loan and immediately make a change. You're requiring the users to have a time limit of ownership before they could implement changes. Would
that's
that
right.
just weird question? What
Yeah.
about the thing that we talked about in the last episode? So if someone's stealing tokens, I mean, I know that if you steal the tokens, you don't have to do any of this implementation, but essentially you can do the same thing, right? You're stealing tokens, you can you have a vast majority of ownership, but you can implement changes too if you wanted to.
Yeah, that's right. Well, you would have two vulnerabilities. You
Yeah,
would have, the first one is the one regarding voting power, and the
yeah.
other one would be the transfer from the minting and all of that. Yeah, yeah,
Wow.
but would be the same. Would be the
So
same, like
I
a
mean, the
like a
best
flash
way
loan.
to yeah, so the best way to avoid this is though having that time requirement, so someone isn't just doing a flash loan and within minutes they have a ton of funds to make these implementations or change these
Yeah,
implementations.
I wouldn't say is the best way, because of course always you can do it better. That is one remediation that can be taking place. Yeah.
Very cool. Okay. Do
Mhm.
you happen to have
And
an
yeah,
Go ahead.
yeah. Sorry, Ben. Yeah, I would like to talk about also an attack that is happening. Well, I wouldn't say every day, but this attack has happened a lot, which is the sandwich attack, which is related with front running transactions. I
Okay.
mean, in first of all, a little bit of background. In Ethereum, you have the mempool. The mempool is visible by everyone. So the mempool is the part of the protocol that the transactions go before being executed. So it is a queue. Okay, you have a queue which is receiving transactions, and then the transactions they are being executed. So imagine that I want, as a regular user, I want to buy tokens in a specific protocol. I don't know, whatever. One thing that I can, if that protocol that is selling me the tokens is well, it's not pretty well developed, uh, I can say the amount of money that I want to put, but I cannot know the amount of tokens that I'm going to receive, because the price of the tokens are being modified every time someone buys or sells the tokens. So I cannot block that price of the tokens. Okay, so I'm going to put some ether, and I'm going to receive the equivalent in that moment of tokens to that ether. Okay, so if I send that transaction, that buying transaction, that transaction is going to go to the mempool. An attacker could check that transaction and say, "Hey, wait a minute, this guy is going to buy these tokens. Okay, this guy wants to buy tokens with this ether. So what I'm going to do is to buy lots of tokens before that guy. So what I'm going to do is to increase when I buy that tokens before the legit guy.
Yeah.
What I'm going to do is to increase the value of the tokens So the guy that was going to buy the tokens, he's going to buy less tokens than he thinks.
So because the
I don't
value
know.
is more, yeah, so the price is going up, you buy less because the
Yeah,
price is higher. By increasing
that's
the
right.
price, you buy less, so that allows them to get less tokens. And if each token is $1, you have 10,000. If it goes up by 50 cents, it drops the
That's
amount of
right.
number you get. Okay,
That's right. But okay, and then the transaction of this guy is executed, and this guy has the tokens that whatever, and now the price has been raised again because this guy has bought tokens also. So the price is going up and up and up and up.
yeah,
And now because I am seeing the transactions and now I can see the actual price of the tokens, I can sell mine. I can sell my tokens. So what I have done is I have put an instruction here, a transaction here. This guy has executed his transaction here, and now I have put another transaction here. So here I have made the price go up.
yeah,
This guy, whatever, but the price has gone upper than before, and now the last transaction, I can sell my tokens at a higher price at the beginning. So I'm winning a delta here, you
yeah.
know?
Because the changing price is what's making a difference for people, right? You essentially are gaining money by selling at a higher price, or you're controlling the market pretty much at this point.
Yeah, that's right. That's right. By privileged information, because I'm seeing in the mempool the transaction of this guy. So
God, okay.
other protocols try to avoid these kind of things. Like for example, in Solana, you don't have a mempool. The transactions are being executed in other way. Um, and also in Ethereum, you can try to adjust that delta that you're willing to pay when buying tokens. Okay, I don't
Yeah.
want to wait for a guy that comes before me and buy a lot of tokens, and then my price goes to the to the sky. I don't want to do that. So I am only willing to pay uh, something more. And that is sleep page tolerance that it's called.
Wow. Okay.
You know.
Interesting. Yeah, it's fascinating to see how it pretty much becomes like a market, right? You just control the price by just having insider information because you can see
Yeah,
it.
that's right. That's right. Yeah,
Wow.
it works well. Kind of similar, well, it's not that centralized, but it's true that you're manipulating the price of the
Yeah.
asset. Yeah, that's
Wow.
right. And regarding, for example, more logical or more technical attacks, if you want to know that, we can talk also about the signature replay attack, for example, which is also a pretty interesting concept. um,
Can you explain what the signature is for people that don't understand it?
yeah, well, in order to execute transactions, you have to verify that you are the one that are sending the transaction. So you have to sign that transaction. I would say that
Kind of like you
it's
sign a check,
similar
pretty
to a
much.
regular, yeah, to a regular sign. Okay, and you have to put your identity there,
Yeah.
and just to make sure that you are the one that are executing that transaction. Okay, that is the signing process, I would say. So in the signature replay attack, it is similar to other attacks in regular IT, and you will find similarities. But let's say that you have a multi-signature protocol, a multi-signature contract. What is that? You need not only one signature, but two or more. I mean, if I want to withdraw funds from a protocol, and I want to do that, because that protocol is based on multi-sig, I have to ask another colleague that has also interest in that to sign that transaction. Well, it's like multi-signature wallets. That means that I'm not the only owner of the
So
wallet.
you have to co-sign pretty much.
Yeah, you
It's like a
are
joint. It's like a
co-signing.
joint account. Yeah, it's a joint account.
That's right. That's right.
Okay.
Exactly. So if you have only one contract that is implementing that, and it's not implemented what we call nonces, and I'm going to explain that in just a minute. You have one contract that is waiting for a multi-signature, well, a couple of signatures, okay, in one transaction. So if it is uh, wrongly configured, you can, and for example, imagine this: one person wants to do something, okay, in this contract, and the other person is the attacker. So the first person send a transaction with its signature to the second person, which is the attacker, and the attacker can then can send again this transaction signed by both users to the contract. Okay, that is the regular functionality of multisig. But if the contract is it's not pretty well configured, you can reply that transaction. So you can send that transaction with the same signatures over and over again to the contract. If the contract does not verify the um, the unique, I would say, what the uniqueness of the transaction. Okay, so if I have one transaction that is going to withdraw one Ethereum from a protocol, I can send it multiple times, and I'm going to withdraw multiple ETH.
Yeah.
Okay, that would be an approach. And another approach is, okay, you can remediate that using a nonce. A nonce is just an identifier um, that specifies that that transaction is unique. You have to specify multiple nonces for multiple transactions. So if I send this transaction to the contract over and over again with the same nonce, the contract is going to tell me, hey man, stop, because you have already sent me the first transaction with the first nonce. You cannot repeat the same transaction. Okay, so it's
So the
something
nonce has to
that
be unique. So the nonce has to be unique per transaction.
that's right. That's right. So yeah, but what happens if we have not only contract but multiple contracts that implements the same functionality, and they are not bound between them?
Yeah.
Okay, now I can send the same transaction to one contract, to another contract, and to another contract. So maybe I can do the same thing with three contracts that are not that are implementing the same functionality, but not are bounded between them.
Okay. Yeah. It's. I'm trying to think about how to even prevent that. How do developers prevent that?
Well, you would create like, for example, a proxy contract that verifies that transaction, or for example, and the easier way, I would say that not implement the same exact functionality in every contract.
Yeah.
So if you
So
have
don't reuse it.
withdraw, yeah, that's right. If you have withdraw Ethereum in one contract, okay, now you are offering that function already. So don't implement it in another contract.
Yeah. Yeah. Yeah.
No, that is a
Interesting.
workaround. Yeah, yeah,
Okay.
that's right.
I'm. You have the gears going in my head right now. But for the sake of time,
Well,
I know you have one more thing you want to talk about. It was the re-entrancy and then the DAO hack, pretty much.
yeah, well, I'm not going to talk too much about the DAO hack. Just mention it, but one vulnerability that is pretty interesting is the re-entrancy one.
Okay.
And I think it's better to see it in the code. But the only thing that I want to say is that this is related with the DAO hack, which is it's a hack that happened in 2016, and well, and because of that, Ethereum did a merge in its protocol. So right now we have Ethereum Classic and the Ethereum network, the regular one.
Yeah.
Well, that fork happened because of that, because the the people were losing their funds, and they did that just to revert the damage. So and this vulnerability, the re-entrancy attack, was discovered between quotes in that attack. So yeah, so it's pretty interesting, and I would like to show you just a little bit of code.
Okay, let's go ahead and share your screen and take a look at it.
Okay, so here we have pretty similar code than the past video, but now we're going to check Nice Bank. Nice Bank is a bank, very very nice. Why? Because it is going to give you free money. Okay,
Very
so
nice. Okay.
yeah. So we have here, the thing is that when you buy things in this protocol, in this Nice Bank, you are not going to have the tokens. What you're going to do is just to move the tokens inside that bank. So I would say that that bank has accounts, and you can move your tokens inside that accounts. Okay, you can transfer them, and you can do whatever.
Okay.
So the thing is that if you check this function here, withdraw all, yeah, you have here constraints. Okay, you here we are checking that, for example, the balance of this contract of this bank is greater than the amount of tokens that the sender wants to sell us. Okay, the withdrawal function is going uh, to buy all the tokens from the user that is calling it. So it's going to, if I'm the user and I call withdrawal, I'm going to sell all my tokens.
Okay.
Okay. So as you can see here, well, this is a spoiler, just 1 second. But as you can see here, we have message sender call. Okay, what does this mean? This means that to the sender, to the one that is calling this function, we are sending this Ethereum amount. Okay? Why? Because the balances of this sender, so the tokens that this sender has in his account inside this bank, uh, that tokens cost Naham price. Okay.
So you're pretty
so
much
so
saying this many tokens times this many price.
yeah, that's right.
Okay.
So we are going to pay. Of course, this is later. In theory, we're going to pay this caller the amount of tokens, and now we are going to set his balance to zero because
Yeah, because you sold
he
everything.
has, yeah, and total supply, the total supply of all the tokens inside this Nice Bank will be we will add the balances of this sender. And sorry, just a second, because here it is.
Okay.
Okay, so what we're going to do, this is not relevant, this order. Okay, so what we are going to do, we are going to compile the contracts.
Okay.
Okay, compiled. And now we're going to execute this test. And I want you to focus on this what is happening here. First of all, we are going to, from a regular user, from the payer, we're going to transfer to Nice Bank. This is the attack preparation, okay? We're going to transfer to the bank 20 Ether, okay? So that way the bank is going to have the funds.
Okay.
So later, we're going to mint to this bank, we're going to mint 5 tokens. So the bank is going to have 20 Ether and 5 tokens.
Okay.
And now to the attacker account, he's going to send 10 Ether to an attacker contract. And this attacker contract, we will see it in just a second.
Okay.
Okay. And now thanks. Okay. So we are going to see that attacker contract in this one is this can be called the exploit of the vulnerability. So as you can see here, well, it's a pretty simple contract. We are importing Nice Bank, that's all. So we are importing definition of the nice bank. This is just I would say it's just a pointer to the bank. So
Okay.
that way we know what is the bank allocated, so we can call it. Okay. We are going to start the attack, and we have the get balance. Okay. The exploit relies in these two functions here. So what we are going to do, first of all, we're going to buy tokens to have tokens in our possession. Okay, for Ether.
For Ether. Okay.
Sorry, we are sending 4 Ether, and we are buying 2 tokens. Okay, because 1 token is 2 Ether.
2 Ether. Okay.
And then we are calling withdraw all. And what is happening here? When we call withdraw all, we are going to call, just follow the flow, okay? We're going to call this function. And this function is going to call this sender that call function, sending us the Ether value that correspond to the tokens that we are selling, okay?
Okay.
But when a contract calls this way, uses this function to send Ether, this contract is calling which is called a fallback function. This fallback function is external and is payable. Why? Because you need a function to receive tokens in your to receive Ether in your contract, and this is the function that is called when you are receiving Ether. Just because when you are receiving Ether, you may want to do whatever, okay?
Yeah.
But what do we want to do? We want to call again while Nice Bank has more than 1 Ether. We are going to call again withdrawal. And what is happening with the execution flow? That we are calling again withdrawal. This is like almost like a Stack Overflow. You know, we are putting one instruction over the other, and always we are going following this flow. We are getting into this call. We are going to this call fallback function, and we are getting into again withdrawal. So we are getting into withdrawal, and we are calling again the fallback function. So if you realize that, we are not modifying the supply, the balances of the user, neither the total supply of the protocol, of the bank, because we are not going further of this function. This is recursive.
So so what you're doing is here, you're just repeating the same thing over and over and over again without going to the next thing that sets it back to 0. So you're pretty much skipping the 0.
That's right. So what we are doing is forcing this bank to, with just 2 tokens at the beginning, we are forcing this bank to send us all its funds, because the bank is not modifying these internal variables, you know.
So yeah, what's happening essentially is instead of getting the money out of your funds, you're just draining the bank.
That's right. And we can see it just executing brownie test minus s. Okay, and well, let me just 1 second. As you can see here we are checking the balances. Okay, and now the only thing that we have to do is start the attack. That's all.
Wow.
And this start attack will call this function called withdrawal. Withdrawal will call fallback withdrawal, and fallback withdrawal, and so on.
Yeah, so, just looping through with that. Okay.
That's right. So we can execute it. And what is happening here is, as you can see, Nice Bank at the beginning has 20 ETH and 5 tokens. Total supply, 5 tokens. Okay, perfect. The attacker contract has 10 ETH. And in the end, look at this, Nice Bank, the balance is 0.
And the attacker has 30.
The attacker contract has 30 ETH. So we have drained all the Ethereum from the Nice Bank, which is a very, very nice bank.
Yeah. Incredible. Okay. You said this was So the relation, the thing that I asked you earlier about the decentralized autonomous organization attack, this is how they discovered. This is how it was discovered.
Yeah, yeah. Well, this is how the re-entrancy attack was uh, publicly known, I would say.
Wow, I'm mind blown by this because the thing is like you see in the news, whatever contract was drained, whatever whatever token was drained, whatever you see all these things in the news, and you always wonder how it happens. And
Yeah,
I know that it's not as simple as this to find it; it's more complicated. But just looking
for
back at
sure.
it, it just seems very much like you just pretty much are skipping things. You find a
Yeah,
logical flaw in a way money is being handled, and you just have unlimited money at this point.
that's
And
that's right. And in this particular example, if you change this order and you change this instructions here, let me just double check it. Okay, look at this. You have
so the
changed the behavior of the attack. Now it's not vulnerable.
So it was just an order of it's an order of operations.
That's right. In this case, it is related with the order. In other cases, it's way more complicated,
Right,
of
of
course.
course.
But in this simple case, just changing the order of you are updating the values after in the vulnerable function you are updating the values after sending the money. So why not update the values before sending the money?
Yeah,
Because you
take the
are
money
going.
before you sell it, right?
That's right. That's right. You're going to do
Wow.
it anyway. So put it before.
Wow, okay. Crazy. Okay.
Yeah.
That's mind blowing, man. That's incredible. That's
Yeah. Man.
awesome. Okay. I've always seen the things in the news and I've always wondered, and this is like a very good way of understanding how
Mhm.
I don't want to overly simplify and say this is so easy to do, but with this example specifically, it's just an order operation. And if you put the two and two together, it's easy to find these vulnerabilities. It's just a lot of pretty much following each money and seeing where it goes within each function, right?
Yeah. That's right. That's right.
Wow.
That's right. Of course, in other protocols and in other cases, could be very complicated. But I have tried to simplify it just a little bit. But this is the
Yeah.
basics of the exploit and the vulnerability itself.
Paul, I think this is probably one of the, not that I haven't learned enough from you so far, but I think this was like the over the top for me. Thank you again. I
Awesome.
think there's more episodes we're gonna work on. I don't think you'll be coming back, but I know we're gonna look at
Mhm.
DeFi next and look at some DeFi examples, which I'm really excited to see. But I want to say thank you so much, man. This was very very cool. It's always nice to have you on these smart contract episodes of the series. I've learned a ton from you, man. I can't thank you enough. Thank you so much for doing this, and I can't wait to see what we can do next together. Hopefully.
Okay, it's a pleasure to come here. So thank you very much, Ben, for having me here.
Cool. We'll talk soon.